The upper tail of the Streamflow distribution provides critical diagnostic insight into catchment behavior. It helps us quantify the magnitude, frequency, and timing of extreme flows that govern flood response. This is where peak flow-based hydrological signatures become useful. In this episode, we will look at the key indicators used to characterize magnitude, frequency, and timing of high flow events, and explore how they can help us to understand and model catchment behavior. Stay with me. Peak flow-based hydrological signatures focus specifically on the high flow characteristics of a catchment. They provide information on flood magnitude, frequency, and timing, and help us understand catchment's responsiveness to extreme rainfall events. These characteristics are particularly important because high flow behavior can be strongly influenced by catchment topography, soil properties, land use, drainage network, storage, and rainfall characteristics. Let's look at some of the key indicators. The first one is annual maximum series. It's the foundational peak flow signature, the single highest instantaneous or daily discharge recorded in each year of a Streamflow dataset, regardless of how many other peaks occurred in that year. Then we sort the series and assign each value an empirical exceedance probability with a plotting position formula such as this. The main strength of annual maximum flow is its simplicity and its direct relevance to design flood estimation. However, there is an important limitation. By retaining only the largest event in each year, we discard information about other significant floods that occurred during that year. This means that annual maximum series may not fully represent the frequency of high flow events, particularly when multiple large floods occur within the same year. Also note that instead of selecting only the maximum flow from each year, we can choose a different approach of selecting all independent flow peaks that exceed a predefined threshold over a period of time. This method, which is known as peak over threshold or partial distribution series, yields a larger sample of high flow events and is particularly useful for analyzing flood frequency and extreme hydrological behavior. However, the results depend strongly on the choice of threshold and the definition of independence between events. The second one is peak flow quantiles. By relating the magnitude of extreme hydrological events to their frequency of occurrence using fitted probability distributions, we can extract our desired quantiles. For example, a Q 5% represents a flow that has 5% chance of being equaled or exceeded in any calendar year. The advantage is that quantile can provide a more complete description of high flow behavior than a single annual maximum. They can also be calculated consistently across catchments and used for catchment classification and model evaluation. However, extreme quantiles are sensitive to the length and quality of the Streamflow record. And importantly, a flow quantile does not tell us whether those high flows occurred as a single extreme event or as a series of events. The third one is peak flow timing. Beside the peak magnitude, the peak timing is also critical. An important signature of catchment behavior is the lag time, expressed as the time difference between the centroid of rainfall excess and the resulting discharge peak. A short lag time characterizes a flashy, fast-responding catchment with limited attenuating storage. A long lag time, on the other hand, characterizes a large, low-relief or highly permeable catchment. The key advantage of this signature is that it directly connects to physically interpretable catchment properties such as size, slope, land use, channel network, and storage. A key limitation is that a single lag time value from a single event may not represent the catchment well, since lag time varies with the storm intensity, special rainfall patterns, and antecedent wetness. Peak flow-based signatures have several important applications in hydrological modeling. Let's go through them. First, infrastructure design and floodplain mapping. Second, hydrological model calibration and evaluation. Peak flow signatures can provide clues about whether a model adequately represents processes such as infiltration, surface runoff, catchment storage, and routing. Third, regionalization and prediction in ungauged basins. Fourth, catchment classification. Peak flow characteristics can help distinguish between flashy and attenuated catchments and identify differences in catchment response. As you saw, the peak flow hydrological signatures characterize the upper tail of the Streamflow distribution, capturing catchment flood generation mechanisms and high magnitude runoff dynamics. In the next episode of this series, we will move to another family of hydrological signatures known as water balance signatures, where we will focus on how water is partitioned within a catchment. Thank you for watching. See you in the next one.